Okay, let's start. Hi, everybody.
Batterie 80%. Connecté à emisiones HP.
Can you hear me? Yeah, sorry. Can you hear me well?
Yes, sir.
Okay, good. All right. So last time we went over most of chapter 2, but there was still a few details to finish. So let's finish this quickly, and then we can start chapter 3. All right. So we all saw that. Yeah, so the conclusion from last time is coal is bad. That's basically it. Yeah, we saw this addressing pollution, or did we? Oh yeah, here we were. Okay. Somebody has a comment. Yeah. All right. So just reminding you what we're discussing so far. So we were discussing ways to address pollution. Technically, by which I mean not economic approach to making sure that this will happen, but rather technically, these are sort of 4 categories of things we may try and to do to improve the situation, or things that will eventually happen if pollution is to be reduced. So we discussed 1 and 2. So briefly, that 1 we said was so reducing growth, or even decreasing the amount of output. And this is it's I would say it's very popular in the environmental movement, and there's even ecological economics, or ecology in general, which sees humans as just part of nature as a whole, and would just like to see economic activity being reduced. The problem with this is it's that so things are rather urgent, so we have to make sure to eventually reduce, especially with respect to greenhouse gases. Time is sort of running out. We're already seeing the impacts of climate change as we go on. Well, this winter is rather cold in Canada, but in general, yeah, it's getting quite warm quite fast. So since people's habit is rather take time to change, maybe in the very far future we can change them, but in the short run, what we need is the most efficient way of changing the situation to making the change that we want to make as likely as possible to actually happen. So this is why, relying on engineering or scientific solutions, such as reducing residuals from pollution production. It's not like economists say, yeah, we know for sure, for a fact, that this is going to happen. Because it relies on the hope that technology is going to happen. It's just that in the past, if you look at food problems, if you look at problems like the hole in the ozone layer, or acid rains, every solution hasn't been, oh, let's stop producing, or let's stop having refrigerators. It's let's have refrigerators, but that don't use CFCs, so that we don't have these residuals. So if we just look at the past, it's much more likely that this is also going to happen in the future, that we're going to probably find ways of reducing residuals from production, hopefully. All right, so yeah, and so this was showing that solar is solar and wind are very good candidates, and now they're becoming extremely cheap compared to other energy sources. But this is forgetting the fact that it's not always sunny and it's not always windy, not everywhere, not always. So for this, we need what? We would need storage, mass scale storage, which is not yet there. Hopefully it can get there. So these are two ways that look promising. Other batteries, there's huge amount of investment in research on batteries, but it's difficult. So yeah, so this is one thing. It requires often specific materials here, like lithium, and batteries may generate other environmental problems, such as because they're they may be dangerous to dispose of. This sort of way would be a gravity is one way, but yes, there are other alternative ways to store electricity. Hydro storage. So if you have a dam, like in Quebec, then you just pump hydro up when you have extra electricity, and then let the water flow back down to use this electricity. So that's awesome. It's just that you need a big amount of water to do it. Yeah. So quickly, so this is just about with respect to lithium-ion. These are the most recent numbers I could find, and yes, the cost is going down quite fast. We didn't have enough. Yeah. So, but it's possible to open the dams if we need more electricity. Yeah. So as you can see, the cost of lithium-ion battery storage is going down, but it's not. I mean, it would be better if it was very, very low. Then there would be no problem at all. Until we get to some very low number, so if we get to a very low number, that's game over for climate change. I think we have a big shot at overcoming the problem. Right now, it's still moderately expensive to store electricity. Yeah, so natural gas is a backup plan that it's not as bad as coal. So as I've shown you here. So in terms of emissions, so gas is there. So you see that the median is so more or less half, or a bit more than half of coal. So it's yeah, it's a good emergency backup. So again, environmentalists really don't care about gas. They say gas is some fossil fuel anyways. We don't want to even think about it. I think it's undeniable that in the US, at least, the shift from coal to gas has been helpful in the last decade to reduce CO2 emissions. But yeah, it's not a long-term solution. It's a backup solution for a while until we get to something better. And by the way, as I've said in Germany, so do I have the numbers for Germany? Yeah. So Germany, it's been going down. Why was it so much higher than France or Sweden? It's because of all their coal power plants. Now they want to shift to what? Gas, but gas from which country? Somebody knows. Yes, so now they want to, Germany is trying to switch at least from coal to gas. So it would be better, I guess, but now they're like not so sure if they want to help Ukraine, or yeah, that's a whole other set of problems. But yeah, so yeah, what would be very nice with the renewables too is that if we were really able to produce them in any country, then all these tensions in the Middle East and in Europe, and yeah, all these international tensions, basically, they would be alleviated quite a lot. So there are also international problems that come with fossil fuels. And plus, we wouldn't have to pay Saudi Arabia all that money, and they wouldn't get all these Canadian weapons to fight their wars. So that would be awesome too. but that's another story. But that's part of it, though. That's totally part of the cost benefit of getting rid of fossil fuels. All right, so here we're back to this. So that was, last time. So yeah, third approach would be, okay, maybe we still produce stuff, maybe we still produce pollutions while we produce it, but let's try to increase recycling. This tends to be quite popular as well, because people don't like sacrificing their consumption, but they're ready to make some effort in using recycled stuff and maybe using their recycle bin. So that's rather popular, and also that's the good way for the average citizen, I would say, to feel like they're a good citizen. So, oh yeah, I did travel to Europe or Cancun or China, or but at least I'm putting my small plastic trash in the recycle bin, so I'm a good citizen, and all is good in the world. I have nothing to nothing to feel bad about. Yeah. So the thing is, yes, Mr. Lucier.
I don't know if this is true or not. I heard some rumors. I know, for example, Montreal does have a lot of waste. It's rather than recycling, we waste a lot more. That means like garbage wise. I think that's pretty much anywhere in the world. But I mean, I know Montreal, it's pretty bad. But I know that there's a way of using those wastes to make electricity. I forgot that's I think it's a gas. Je sais pas si une gaz
Yeah,
de-
biomass gassier.
Yeah, exactly. So I don't know if it's, in a way, I know that we do pollute in a way a lot, but wouldn't that also be a way of reusing whatever we waste into something that could be useful?
Yes. So I've put statistic on biomass too, so that those are here. So you see, it's still it's still has emissions, and it's still dangerous for human health. But I mean, it's better than nothing in some instances, I guess. Yeah, and so in the Scandinavian countries, they're quite heavy on biomass. But all in all, the thing is, it's difficult to recycle, and it's not. So it would be better to not have trash in the first place, rather than. And so yeah, so these are the problems with it. So you need not all goods can be recycled. It needs coordination. One thing that people are pushing for is at least create goods that can be recycled easily. So if you're having one sort of container with plastic, at least just use one type of plastic and do not wrap it around many stickers and things, because everything becomes so complicated to recycle. It's just very, very basic things like this. Yeah, so one thing last class, I thought I had read about Apple's recycling program, and I thought it was very, very nice, like the best recycling program that all computer manufacturers had. However, I dug a bit deeper. And the problem with Apple's is they are very good at making you recycle your old computer, because they want you to buy a new one. So there was on the CBC, I think there was a TV program. Let me try and find the what was the number they had. Oh yeah. So there's a journalist who just who had something that didn't go well with his computer screen. So he went to the Genius Bar, and so the person took his computer back and looked at it and came back and said, yeah, so it's going to be at least $1,200 to repair it, or if we have to change the screen as well, so it's $1,980. And he said, yeah, but I just, there's just one small flickering there. No, but you had water inside it, so it's damaged. You have to change everything. And then he said, okay, well, let me have a second opinion. So he went to an independent repair person, and the man looked at it and he said, oh yeah, I know it's the pin is wrong. Let me just fix it. And he just opened it a bit and unbent a pin that was going to the screen and put it back in, and voila, perfect. So he said, so how much would that cost? Oh, it's free of charge. I didn't, it took me 5 minutes. I'm not going to charge you that. So yeah, he goes to Apple Store and the Genius Bar, and they say it's going to be either at the minimum $1,200, and then then he goes to this independent worker and he say, yeah, no, it's 5 minutes, it's free. So yeah, that's it's easy to recycle if you're recycling computers that would be still perfectly good for using. So yeah, I think they're making progress right now, but yeah, the right to repair is something that's complicated, and that's in many different spheres. So for instance, in the farmers are asking for this too, because yeah, it used to be that a tractor was very easy to repair and everybody could do it, but now they are very complicated, and they have a hard time repairing their own stuff. But then if you have to change them every time it breaks down, then that creates more trash. So yeah, so improvement. To have right. Oops. Right to repair. All right. So yeah, recycling is possible, but it's not all that easy. And by the way, I've lived in, so I don't know, maybe I told you that already, but yeah, I lived in Geneva, and they had a recycling and a compost program back in 2005-06. So I thought that would be quite common everywhere in the world, but yeah, it looks like in many places in Montreal right now, we still don't have composts at the city level, so it takes time. So looking more specifically at one challenge is plastic. So the problem with plastic is it comes in many varieties. So you have acrylic, PMMA, PC, PE, PP, PETE, PVC, ABS, all these things. And the thing is, so recycling one or the other could be done in some ways quite efficiently, but if they're mixed together, and the thing is, in the recycle bin, they are, it makes things much more complicated. And if as soon as you mix many of them, then the quality goes down very, very fast. Yeah, so you would need to have a way to sort them, but there is so I've looked at it, and there is some progress on the horizon. So this was a recent article in Nature in what year? It's quite recent, a few years ago, about this. It's a French startup called Carbius that are developing enzymes capable of breaking down plastic and making them mostly all the same type, so all PET. And then they can recycle them quite efficiently. So we can make progress on this. Was a nice analogy I've heard with wood. If you think about where all the coal reserves in nature come from, well, they come from the first time that wood was created by nature. And the thing is, before we didn't have wood, and then all of a sudden there's one plant that invents wood, and then they can grow much better and taller than the other plants, and they take over. but then nature had no idea, no way of breaking down the wood material. So they just grew and grew and grew for thousands and thousands of years, and they piled up all the dead wood on top of each other until at one point it was finally some fungus invented a way to break down lignin. I don't know what the name is, but anyways, the wood material. But then by then it was all compressed, and that's what created all the coal reserves that we now have in the world. And plastic is about the same thing. We've never had this stuff in nature, but it's for sure if we just waited a couple of thousand years or million years, then nature would come up with many ways to break this material down. It's just we don't have that much time, but it's perfectly possible to accelerate the process and figure out ways to break down plastic, but it has to be done. So yeah, maybe all the best for Carbius. I hope they succeed. Sorry about that. And then lastly, so waste treatment. So this is if you didn't even make any effort to recycle or reduce the waste that you dump in the nature, then there's one last resort solution is just to try and decontaminate whatever you can. There's one, I guess, upside to that is you know what you want to do. So if you want to decontaminate one terrain somewhere, then that's what you focus on. But yeah, it's really a solution of last resort. It's much less efficient. So if you think about greenhouse gases again, so think about the difference between capturing carbon emissions just outside of the factory where they are emitted before they go in the atmosphere, or just trying to catch some CO2 molecules in the atmosphere. That's just a whole other set of problems. Yeah, so we may recuperate some material from landfills, but yeah, it's better to not put them in the landfill, and it's tends to be quite a bad job. So if you think about the fact that we send all our electronic products in some third world countries, and there maybe children go in the trash and try to take out some precious metal out of it, but it's horribly bad for their health. So yeah. Oh yeah. So food waste is it's an interesting topic. Food waste. Because in a way we have more food than we need. The thing is we throw it away. But if you think about it, if you so what's bad about food waste? If it just so if methane comes out of it and that creates CO2 or not CO2 but greenhouse gases and contributes to climate change, then food waste is bad. But imagine I'm just going to have just a philosophical idea. So imagine that nobody is poor, everybody eats at their fill, and we waste half of our food and it goes in the garden in compost, for instance. Would that be bad? I don't think it would. So in a way, food waste is some sort of side effect of food being something that we like eating fresh. And so if we have the choice between a slightly rotten apple or a perfectly new one, we just always pick the new one. So the problem really with waste is if it creates greenhouse gases, and if in some ways we would be able to take the food before it goes bad and give it to people who don't have it. Yeah, Mark, go ahead.
Yeah, I agree that I think the issue is not necessarily that there's food waste, but it's also how we manage the food waste. Like if you said, if we're using it for compost and like for to reuse for planting, gardening or whatever, it's fine. But then you have the cases where it's just left at the dump site, tossed away, and then causes problem with the greenhouse gases. So I think
Yeah.
it's more the management of food waste.
Yeah, I see. I think there's in every day, like for people in general, they look at it and they see, oh, but I just threw away an apple that was a bit rotten. And by the way, I've seen somebody was hungry last week. So somehow I could take this apple and give that to that other person, and that would be better. The thing is, economists, we don't really think that way. We think, so how is the best way to make sure that person that was starving get food? If it's easier to just produce more food, then you just produce more food. And how do we make sure that the food that we throw away isn't a problem? So as long as it doesn't produce methane, so we don't really care about, so it's just part of nature. If you think about in nature, you have trees wasting, having their leaves fall in the fall. So do some, but in a way, it looks wasteful. You know, you had a perfectly nice leaf, and then all of a sudden it just falls down. Well, it's part of what's being a tree and having leaves. And the leaves go in the ground. And in some ways, it's bad because these leaves rot and create CO2. So it's bad for climate change too. So I mean, all I'm saying is we just have to be pragmatic about what we think is important. So we think giving food to people who are starving is important. So do it in the best way possible. Maybe it's by reducing waste, or maybe it's just by producing more food. And you don't have to judge whether one way is best than the other. Yeah, Mark again.
Well, I know that to reduce some food waste, some places try to create like food banks where they take food that's close to the expiration date and then selling it at a lower price to maybe for families that have lower income. So that's another way to reduce food waste.
Yeah, so if you can do that efficiently, and I mean it, so yeah, okay, let's going a bit further into this. So what's the problem? Why would all the restaurants and Tim Hortons, and why wouldn't they give their donuts away? Or, well, because of course they're scared that that people are just going to wait for the store to close, so they can just instead of buying a donut, they can just have it for free. Or even if you think about clothes, is the same thing. So big clothes chains like say Gap or others, they throw away so much of their clothes. Like as soon as there's a new season and they figure out that they can't sell the old clothes, then rather than give them at lower price, they just throw it away. Because for them, the clothes has no value because they can't get anybody to pay for it. But yeah, so that's actually that's an interesting economic problem. I haven't looked into this, but it looks wasteful. Actually, that's for sure. So if you okay, in economics we have this thing called the first best, second best, third best. So if you could imagine a first best outcome would be to throw away no food or no clothes whatsoever that can be used by somebody who needs it. Then the second best is in the real world, what's feasible and what policy can you implement to improve the situation. So in that way, of course, if you have food banks or if you have some recycling program for clothes that can be implemented while the stores sort of agree with it, then for sure it's better than throwing them away. So yeah, that's not something I should maybe look further into, but I haven't read too much about this. There was a question, comment?
Yeah, I just had a comment. I thought it was worthwhile that like a big problem of of waste is that I go to Sinaloa sometimes to visit family, and I was talking to this farm owner, and apparently they have this thing called aesthetic selection, and they like go out, like let's say an avocado is ugly, like it has a deformity or something like that, they simply throw it out instead of
Yeah.
like that's I know, I thought that was interesting. If someone could solve that problem, there'll be a lot less waste.
Yeah, so the thing with this is, I think the free market could do it if they were smart, in the sense, and I'm pretty sure they do it, in the sense of, well, if you're, I don't know, your avocado, it looks weird, but you can use it in guacamole, for instance, because then when you go and buy the guacamole, you have you can't see how the original avocado was shaped. Then some private firm should do it, and they would make money out of it for sure. They would use the badly shaped fruits and vegetable for something, and the good shaped food and vegetable for some other purpose. Yeah, exactly. So that's part of buying stuff, is buying something that looks nice. That's just people's psychologies. And yeah, there's also one way to do it is, so I know that the brand of Apple called Pink Lady. So how do you, so Pink Lady is like just in between green and greenish red. So they are like sort of pink. And how did they manage to create this? Well, their apple variety does produce this type of things more than other sort of apple, but mostly they just decide when they get their apple, they decide, oh, that's the right color, so this is a Pink Lady. That's not the right color. So it's another less expensive apple, and they choose whether. So at least the less expensive apple, they don't throw it away; they just sell it. But yeah, Pink Lady is just some other apple that it's exactly the same, but the color is a bit different. Anyways, that's consumer psychology for you. But if you like eating a pink apple, then. Yeah, so one thing that is said often with this too, it's once you say, yeah, we can increase waste treatment, so that can be used as a argument by industry to not do anything. So so that's not economics, that's more political. That's but still that's part of the game. So here is one yeah, maybe one of the most advanced effort, that this is in Switzerland, to capture CO2 out of the atmosphere. So here they're able to remove carbon dioxide from ambient air. It's powered by wasted heat from a garbage incinerator, so it looks nice. But so the cost right now per metric ton of CO2 removed is $400. So don't read this right now, but $400. There's something wrong with this number. So for that, you have to remember and that's going to be a good point for the next chapter, but the chapter after that. Someone has an idea what would be wrong with this cost? So what this says basically is that it's not free, even though it's powered by wasted heat. It still costs a lot to build all this stuff and operate it. Yes, it's very expensive. Somebody remembers from last class, what was the cost per ton of carbon? Or the monetary damage that is sort of agreed right now. So yeah. Why is this? It's too big. So it's approximately $30 to to 51. So $30 is mostly what if you set the median of what economists have been able to compute. So if you add up all the costs generated in the future in terms of climate change and damage and extra catastrophes and all of that, 51 is what the Biden administration just decided they would use as their benchmark numbers. In Europe, it's sometimes they go up to like, I think maybe 70 euros. So yeah, it's in this ballpark. So 30 to $70 or euros. So that's 400. So what you're doing is you're paying $400 to alleviate the damage of say $50. So is it good? No, it's totally wasteful. And yeah, so there was this open letter signed by many experts and I think Nobel Prizes. So it's time to end carbon capture of climate policy. US and Canadian leaders. So they basically say in their letter, carbon capture and storage is unnecessary, does not work, is not viable at scale, is risky, benefits polluters, and justifies inaction. So yeah, this is really something that's not too promising. All right, so that's it for setting the agenda. This thing, we're going to see it quite often in this class. So the whole goal of climate policy and economics in general is to look for the most cost-effective interventions and make sure that they are preventing the most expensive damage that's being caused. And so yeah, we are looking for efficiency here. We are looking for alleviating damage. That's our economic definition of improving the world. It's not making yourself feel nice because you put your plastic bottle in the trash. It's looking at what the big problems are and what the efficient ways of dealing with them are. All right, questions about this chapter so far? So that's the end of this chapter. No, all right, so we can start the next chapter. All right, so this is a big revision of all macroeconomics. So it's not exactly climate science, or not climate, it's not climate science at all, of course, but it's not even environmental economics per se. It's supply, demand, and aggregation, marginal willingness to pay, marginal cost, total cost, all of these things. But it's to set the table for, so if you struggle with this, then make sure that you practice and you read to make sure that it's okay, because these tools are going to be very useful for the rest of the class. Benefits and costs, demand and supply. So first definition, willingness to pay and inverse demand. So what is the value and the willingness to pay? Well, the value is whatever something brings you as happiness, and if it brings you happiness, then you're willing to pay for it. Basically, that's our big definition. So the willingness to pay is related to the value that somebody puts on some good. So it's fundamental notions in economic. that individuals have preferences for goods and services. So that's why they're ready to part money and to buy them. And so given a choice, they can express their preferences for one good over another good, or some bundle of goods over another bundle. And yeah, so what mediates their choice is going to be, of course, the price. And here the preference over one good over another good will be expressed in terms of demand by also the fact that one good is maybe more expensive than the other good. Yeah, so the value of a good that to a person is what they are willing to sacrifice or to pay for it. So what determines a person's willingness to pay? So many things. So, oh yeah, by the way, something that's quite tedious in this class, but I've realized that we can't really avoid it, is many acronyms. So sorry about this, but so yeah, you're going to have to, I'm going to, as much as possible, tell you what they are. So say something like value. So willingness to pay is WTP, for instance. So you're going to get a lot of that, but that's helpful because you're going to have public good, private goods, private willingness to pay, social value, damage, marginal damage, all of these things. So at some point, you really need to be precise when you discuss some concept, otherwise we get lost, basically. So yeah, so I'm going to use a lot of letters in this class. So what determines a person's willingness to pay for goods or services? So individual values, so what you like. Some people are willing to pay a lot for a quiet, clean environment, for instance. Some other are not. So if you don't mind hearing a lot of airplane noise, then you can live near a Dorval airport and you don't care. But if you prefer more quiet environment, then you're willing to live farther away and pay more. So that's why if you go to check a house in Dorval, then make sure that you go at some time where there are flights around, so you can hear how this sounds. Otherwise, you might be ripped off because you buy your house and you don't realize that it's it's not a good place. And then ability to pay. So if everybody had the same ability to pay, that would be much simpler, because then it's just, if you're willing to pay more, it's just that you like it more, and it makes sense to allow people who like it more to pay more. Problem is some people have much more wealth than the others, so it's part of their consideration when they decide that they want to buy something. And it's part of the reason why people may think that economics is unfair in some ways, because yeah, rich people can afford everything, even if they don't really care about for it. But yeah, that's life. Okay, so we normally express willingness to pay as in a graph. So here I've made a graph with discrete quantities. So we're not going to have discrete quantities for long, but it's a nice way to set things set things up. So what's going on? Well, so the question is, how much am I willing to pay for my first organic apple? Well, you look at, so yeah, if I have, this is, if I have 0 apple, what's my willingness to pay for the first apple I would buy? So it might be $5 because I really like apples. And then I eat it, so I have one in my belly, and then I ask what's my willingness to pay for a second one. Well, I'm not too thrilled about as much as the first one, but still I really like Apple, so I can pay $4.50 for it. Then third Apple, I pay $4 and 5, 6, 7, 8, 9, 10, and then after 10, I have my fill and I don't want to pay anymore, or after 9 rather. So for the after 10, I don't want to pay anymore. Is my graph all right or not? This is 3, 4. Sort of weird, no? Why did I draw this like this? It's like 450. Okay, so it's like if I'm anyways, it doesn't matter, but it's like if I should have like one thing here at 5. Yeah, okay. Anyway, so so we're not going to have discrete things because they're a mess to work with. We're just going to have continuous quantities. But that's something maybe for those who had me as a teacher in microeconomics, I may have told you. So when the economists say, oh, but don't you know, people think in terms of marginal costs and marginal quantities. So they think at the margin. So it's not true. Because most of what we can buy, they come in bundles. So we can buy 2 liters or 1 liter of milk, or 1 apple, 2 apple, 3 apple, or kilos, for instance. So why do we use continuous quantities? It's just because it's much easier to model, to deal with. So notion of diminishing willingness to pay. So why do we like less apples? Well, we just assume that that's what people, that's how people behave. It's not true for every good. So for instance, if you had addictive good, then maybe once you give them 1 dose, they want even more. But for most good, we assume this. Yeah. So yeah, this is what I just told you. So we assume that people consume fractions of items, not because it's true, but it's because it's just so much easier to work with that. Yeah, so the demand function is a smooth willingness to pay curve. So example of linear demand would be that would look like this, for instance, but in a linear way would be this. So these are 2 important terms. So linear demand curve is a function of, so it's quantity. Why are you doing this to me today? I said small. Yeah. All right. Okay, I know. So it's quantity as function of price. So I am going to write it this way. So Q is the quantity, and then it's called a quantity that consumer wants. So Q demanded. So that's NDCD as function of price P. So it's really to say that to imagine that there's some sort of causal relation from P to Q. But I can flip the thing around. It's just that when I manipulate Q, I like to know that it's a function of P. But I could very much write it the other way around. So inverse demand. And in that way, so what would the inverse demand be? So that would be price as a function of quantity. And you would write it this way. So how do you go from one to the other? So you just write Q equals 10 minus 2P. So you can just, oops, so you add 2P on both sides and subtract Q on both sides. So you get 2P equals 10 minus Q. So you get P equals 5. So I just divide by 2 on both sides. So 5 minus Q over 2. So sorry for people who think this is too basic. I just want to, who knows, like there's generally a diverse level in this class. So I want to be things to be clear for everybody. And yeah, so the environmental economics class is something that sometimes students that are not in economics take. So yeah, so I'd rather go over the basics to make sure that everything is clear. So that's how you go from this to this. So why do we use this inverse demand? Well, because of some economist named Marshall. We invented the Marshall demand curve, Marshallian demand curve, and he decided to put the price on the vertical axis and the quantity on the horizontal axis, so a bit like this here, price on the vertical axis and quantity on the horizontal axis. But usually we will represent this as the independent variable here and the dependent variable here. So here is the function of this variable. So that's why we show this way, price as function of quantity. All right. And by the way, just for if you remember your microeconomics, so if there's a minus here, it means which type of good is this? Somebody remembers? Substitute? No, not exactly. Yeah, it means that apples have substitutes, so that's why if the price goes up, then quantity goes down. But so name of good with negative demand curve. Yeah, maybe it's something that I don't think it was in the notes and my microeconomics 201, but it's something I said in my group. So it's called ordinary goods. So if you hear about this, it's ordinary goods. As not to be confused with normal goods, which are goods that you consume more when your income goes up. So here it's goods that you consume more when their price goes down. But this is just an aside. You don't have to learn this. So this is what my linear inverse demand would look like. P of Q equals 5 minus Q over 2. So I'm not going to confuse you anytime. So I'm always going to put price here and quantity here. A comment I have here is this here. I put price per kilogram. So yeah, maybe I should have put the kilogram here. So this is the right unit because that's how much you're willing to pay per extra kilogram you buy. So it's not the total price you pay. So this is yeah. So I'm not going to, I think, remove points if you don't put absolutely exact units, but I will. It will make me more happy. So if you put the right units. And, you know, if I'm happy, maybe I'm more inclined to give more points. So yeah, think about this. So does that make sense? Is there a question about this unit there? Right. So it's not the total amount paid, but it's the amount paid per kilogram. Since here we are adding kilograms together. All right. Yeah, so what we're going to say is that the marginal willingness to pay, this is more a technical thing, but yeah, it's so margin MWTP is the point on the demand curve, on the inverse demand curve that shows the marginal willingness to pay for a next item. So for instance, what you would say is, so let me just have, so for instance, if I'm at a quantity of 2, then what is my marginal willingness to pay for 2 or for an extra quantity of apple? Well, it's $4 per extra kilogram. All right. So that would be 4, for instance. So it's affected by many things. How many of the same items somebody already has. So if I have just 2 apples, I'm willing to pay 4 per kilo, or just 2 kilos, I am willing to pay $4 per extra kilo. If I have 8 kilos already, I'm just willing to pay $1 for the extra kilo. So yeah, and I could have 7.02, and I would have it would give me a value too. So yeah, it's affected by this. It's affected by taste and preferences, income, as we've said, time and situation. So this is a quote I like. Somebody, a fan of Shakespeare there. So that's a famous quote from his play Richard the Third, when he falls in battle, and he thinks he's going to get killed because he doesn't have a horse anymore. So he shouts, a horse, my kingdom for a horse. So who would think that the kingdom of England is worth a horse? Well, the king in this particular time and place under a battlefield thought that, yeah, he would gladly trade his whole kingdom for at least having a horse and not dying. Yeah, so time and situation. All right. Yeah. Total willingness to pay. So total willingness to pay is the addition of all the willingness to pay. So it means that if I have been willing to pay this amount and this amount and this amount for each extra apple, then my total willingness to pay for, say, 2 apples is everything that I was willing to pay until this point. So it's also if you were to ask me, I'm going to give you 2 kilos of apple, what is the maximum dollar amount you're ready to give me for this? I'm not going to give you because I want to make to tell you because I want to make a good bargain, and never. So if a seller says, "Oh yeah, what's your highest price?" Never say it, because that's what is going to make you pay. So that, but in principle, you have one. So what's your highest price for, say, 2 kilos? It would be It would be the integral. It would be all of the marginal amount you were willing to pay. So maybe it looks abstract this way. So if I go back a few slides before, you can really see. So what would be your total willingness to pay for, say, buying, say, 2 apples? It would have been, so yeah, 5 plus 4.50, and then you have 2 apples. So it would be $9.50 in total. And for 6, then it would have been 5 plus 4.50 plus 4 plus until you until the 2.5. So it will be the total, the sum of this. All right. So that would be that's easy to see if you have discrete quantities. If you have continuous quantities, it looks more abstract, but it's the same idea. It's an integral. So I swore to you that you would not need calculus in this class. So it's true, but it's just, so I'm not saying that you have to understand what's going on there, but for the math inclined people, so just know that the total willingness to pay is just the integral from 0 to q of the marginal willingness to pay. It's exactly the same as doing the sum. So it's just the sum under the curve. So if you have a continuous quantity, then instead of a sum, you have an integral, but it's the same concept. But so don't care about this, because why? Because I'm always going to give you nice triangles, nice linear functions. So if I give you nice linear functions and you need to know what's the shape of this shape, rather the area of this shape, then you can just compute it quite easily using triangles and trapezoids and this sort of things. But if you add a curve there, then you would need an integral. Yeah, so it's calculated by finding the area under the demand curve. Yeah, so this is what I'm saying here. So I will be nice. So I will only give you linear demand functions of this sort there. So yeah, so where A and B are positive real numbers. So something like this that I give you. So PD is 5 minus Q over 2. So if it's that and you need to say compute the area under the curve, then it's quite easy to do. Yeah, maybe I could make you practice. So if I were to ask you what is the total willingness to pay for 8 kilos. So yeah, question. Total willingness to pay for 8 kilos here. So it's never too early to start computing areas of trapezoids. So what I want basically is the shape of like the area under the curve until we get to 8. So please compute it and tell it in the comment. So you don't need an integral to compute it. Yeah, I'm happy to be asking you this just to make you do stuff. I've been talking for a while. 48. I don't know. I haven't computed it. 20 if you do the whole triangle. Yeah. So the whole triangle. Oh, yeah, we can do it many ways. So yeah. So the whole triangle would be so easier. So the whole triangle, so the total willingness to pay for 10, which would be the area of the triangle. So that's 5 times 10 divided by 2. So that's 25. And then what you could see is, oh, what I just then need to remove that small triangle from it. So that would be equal to, and then this would be 1 times 2 divided by 2. So that's just 1. So is that it? 10 minus 8, it's 2 times 1 divided by 2. Yeah. So that would be, so total willingness to pay for 10 could for 8 could be 25 minus I said 1 times 2 divided by 2, so that's 24. Yeah, but I'm going to show you a better way. Trapezoid formula. It's so h plus small h times or let's just say, yeah, how can I express this? Okay, let me draw one. So this is H, this is big H, this is small h. This is S. So this is just height, side times S divided by 2. Hope it's that, if I remember correctly. So here I would get so 5 plus 1 times 8 divided by 2. So so that's like 6 times 4. Yeah, so it's 24. All right. So okay, I'm not. I still remember my computation from last time. Right. So every time you need a. So that's the two things you may have to compute is areas of trapezoids and areas of triangle. And triangle formula, of course, is so it's base time height divided by 2. So that's quite easy. All right. So good to think about mathematics for a while. Yeah, so you're going to have some math to do, but they will be something like that. But it can get, I'm going to be honest, it can get a bit tricky. So that's why I'm going to give you many occasions to practice. All right, so this is what we were saying. Oh yeah, so it's here. All right, so PD of 0 plus PD of Q times Q divided by 2. Yeah, so that's just what we did so far. So PD of 0 plus PD of Q, so if Q is 8, times Q, which is 8, divided by 2. Yeah, so simply that's the trapezoid formula. So here it's perfectly fine to just learn it by heart and apply it as much as you want. Oh yeah, so here I'm doing it with 5. So it's 5 plus 2.5 times 5 divided by 2. So that's 18.75. So this is the total willingness to pay. And it's going to matter when we consider, for instance, total damage or total abatement costs or many different sort of costs that I'm going to introduce. I'm mostly going to have these sort of linear functions. So when we compute damages, it's good to know them. All right, so this is the discrete example, just something that I gave you earlier. So number of apple 1, you're going to pay 1, 2.6, 3.5, 4. So here, is that linear? No, right? Because there's 1, then 0.6, 0.5, so there's a big jump there. So in that case, if it's non-linear like this, then you don't have any choice, you just add them all together. So the total willingness to pay is just the sum of them. So 1 is 1, then 1 plus 0.6 is 1.6, then 1.6 plus 0.5 is 2.1, etc. So total willingness to pay is the sum of what you were willing to pay for each unit. And then you can compute the average willingness to pay too. So I don't think we use that all that often or ever, but yeah, here it is. So all you have to do is divide the total willingness to pay by the number. So divided by the, yeah, you see how it's useful to have acronyms. So it's total willingness to pay divided by quantity. That makes things easier. All right. Aggregate demand curves. So this is when things get a bit tricky. So I think it's nice to finish with this and then start again with this next time, so it had time to marinate in your brain. So that's why do we need this? Well, because everybody is different, and some people are willing to pay a lot, some people are willing to pay less. So when we aggregate them, we have to aggregate them in some specific ways. And later, we're going to do the same with marginal abatement costs. Why? Because some firms for some firms, it's very easy to reduce pollution emissions. So we want to ask them to reduce a lot. And for some firms, it's very expensive to do so. So for them, we want to ask them to reduce less. And the way to aggregate all the information on the market will be to will look pretty much like this process here. So that's why we're going to that's what we're going to see there. So yeah, the aggregate demand curve is the sum of individual. Yeah, it looks funny, but it makes sense. Individual demand curves for a specific product. So what you do is you say, oh, so if the price is say $4, then that person is going to buy 2 apples, that other person 2.5, that other person 1.6, and you add them all together. So it means that you are adding quantities as function of price, okay, and not price as function of quantity. So this is the most important thing. So you're always adding quantities, unless I say so. So I'm going to tell you at one point in this class, you don't add quantities, you add prices. But for most of what we're going to do, you add quantities together. So an aggregate demand curve is for a private good is the horizontal summation of the demand curves. Yeah, there's a mistake there. I should have said, well, it's not a mistake, but I should have said of the inverse demand curves. Of all the people, because it's actually the addition of the demand curves. So it's the horizontal addition of the inverse demand curves. Yeah, so group by geographical area, region, well, who cares? So you add people up. So yes, it's horizontal because we add them on the horizontal axis, but this is when you add the quantities together. And then when you want to find back the inverse aggregate demand curve, then you invert back this aggregated demand curve, where Qi of P is the demand curve for one person in particular. Example. What time is it? Oh yeah, we're over it. All right, so next time is, I'm sorry, it's going to be quite tricky because we start with something that's a bit tricky, but here we are. Yes, of course. So I'm done with the last chapter, so I'm going to post it, and we're going to continue here with this. All right. So questions, comments? Yeah, so this Concordia, I think, is back in class for not too soon, right? I think it's in February. So for sure, next class is, I think, in still online. Just look at what they're saying there. Return to campus plan. So Okay, yeah, so we resume in-person teaching on February 3rd. So that's, yeah, so this 26th is still online, 31st is still online, and February 2nd is still online. Yeah, so it's the 3rd. Oh yeah, that's what you were saying there. So yes, after. So first class will be on the 7th. Not yet. Yeah. But after this chapter, you're going to have some more homeworks to do. So yeah, probably next time you have homeworks. Have a nice day. Okay, so I see you in 2 days.